Okay, welcome everybody. Welcome to the second offline lesson for the reinforcement learning course. And today we're going to talk about probabilistic reasoning and learning over time. Before starting, however, let me highlight for you the Slido code, which you can use before and during the in-person class in order to ask questions, clarifications, and whatever you need to be clarified. Okay, so what does it mean to be reasoning over time? It means to be reasoning about some systems that evolve over time. So, for example, last week we talked about static systems where we had random variables in a bias network, and these random variables, once they got a value, they kept that value fixed unless you started a new event. Now instead we're going to consider systems that will evolve over time, and then we'll consider random variables whose values will change over time during one single episode, during one single event analysis or observation. So in order to perform any kind of inference, we need to be able to model and understand what are these changes. So in practice, we are actually dealing with dynamic systems like robots or trading systems or systems for spoken language understanding. So here I have an image of the robotics case. So if a robot is moving in an environment, of course this will be an example of a dynamic system was values are changing over time. For example, the position of the robot, the state of the robot, which will be our random variable x, will be evolving in time, which are highlighted here, here, here. So you can consider time in this case like if you were taking some snapshots of this system evolving over time and freezing the system at different snapshots. Okay, and this can be done for several random variables. So for example, here we're considering the robot state x, robot state, but we can also consider z, so observations. Okay, so this is the case with this one, for example, this one, and this one. Okay, so now that we have a clear idea what we're trying to deal with, we can start giving some definitions. So the first definition that we need to give is the definition of a dynamic system, and again we already gave it basically, and this definition is a system that evolves over time. And as I mentioned, you can see this evolution as a sequence of snapshots that start at time equals 0, and then they have fixed interval. So is this realistic? Might be a question. The answer is yes and no. It's up to how you are implementing your system and how you're dealing with it. I mean, of course, real-world systems don't have this kind of slicing. They don't have fixed intervals and these kind of things, but you can try to get data at fixed intervals. You can try to control your system at fixed intervals, so you can try to get as close as possible to a situation like the one which is being described here. So when we have a dynamic system, we represent its evolution through something that is called declarative representation model. So a declarative representation model encodes, first of all, knowledge about how the system works, and it's described in a computer readable form, so that it can be used by algorithms, typically using, for example, something that you'll see being called transition matrix or observation matrix or something like this. So as you're noticing, I'm talking about transitions, transitions between states, exactly because a dynamic system is composed of states, observations, and then a state transition function and observation function. So what are these things? So the state is of course a description of the current situation of the dynamic system itself. So this is XR state. Observations are what you can actually see about that state or something that is generated by the state. So what an external manifestation or an external view of what is the state of the system itself. Then we have state transition functions. So those are functions that map states to states. And finally we have an observation function, which is a function that maps a state to an observation. So let's look a bit at this diagram over here. So as you can see, here we have our current state. This current state is fed inside a transition function. So here the transition function is called f, right? So this is fed inside the transition function, which generates a new state, xk plus 1. So this becomes, after some time, the fixed time interval that we talked about before. It becomes the current state, and this loop keeps happening. In parallel to this loop, we have another loop that takes the current state and feeds this inside an observation function. From this observation function, we get our new observation. So going back to the robot example that we have in here, all of these are the observations, right? All of these are the observations. These are the states. And this is what occurs thanks to the transition function, while this other thing is what is generated. Actually, this is not visible. Let me change color. Gray. This is what is generated by the observation function. So it's something that is mapping this state, so this position, to an observation. So let's go back to this. I want to add something more here. So you're seeing here a notation which is typical of control theory. So this notation where x is the state, z is the observation, f is the state transition function, and h is the observation model. More commonly in reinforcement learning, which is what we are caring about, we have a different notation where S is the set of states, capital S. O is the set of observations, which in reinforcement learning you will see S and O will be the same thing. then we have a state transition function, which in reinforcement learning is typically noted as t, and an observation function that again you don't have really that in reinforcement learning because the state and the observation coincide. So, what I want to add in addition to this is that this transition function can be a function of several things. For example, here, in this case, as in this diagram, as you can see, you are getting a new state just directly from the previous state without any external intervention, if not some noise that we can neglect. So this is something like this state. So it's a mapping from, sorry, let me delete this. It's a mapping from state to a new state. A reinforcement learning instead, typically transition function is something that maps a state and an action to a new state. But we'll see this more in the next classes. Okay, let's move on. So, as I mentioned, at each time step t, the system has some random variables xt that compose the state. So this can be one single random variable, or it can be composed by a different set, multiple random variables. And what is very relevant for us is the fact that these random variables can be either observable or unobservable. So this is exactly what I was mentioning here. So in reinforcement learning, in the systems that we use to describe reinforcement learning problems, the whole state is observable, which is why the state and the observation are the same thing. This is not always true in general dynamic systems, where you can have unobservable parts of the state, and there is no way generally where something which is observable becomes unobservable, and vice versa. So typically you have systems that are fully observable, where all the variables are observable, and partially observable systems where some variables, fixed variables, are unobservable. Okay, so let's look at one example. Let's say you are wondering whether outside it's raining today or not, but you're stationed underground. So the only thing that you see from the external world is a person that comes in your room with or without an umbrella. So what are here the observed and the unobserved variables? The answer is pretty simple, because we are observing only the random variable umbrella at time step t, so whether the person has come in with an umbrella or not, which is Boolean, and the unobservable variable, which is the real state, is whether it's raining or not. Okay. And of course, you can imagine this, that there is a mapping between states that depend on each other. So this is our transition function, rt minus 1, rt, rt plus 1. And this and this continues over time. And these real states generate some observations. So this is why you see out ut minus 1, you have ut and ut plus 1. Sorry for the bad drawing. here, but I hope it's clear enough. Okay, so we already said this like informally, but let's give a definition. Given some random state variables, how do they evolve? We say this through the state transition model, which again we call either T or F. Right? And this specifies the probability distribution of being in a certain state given the sequence of all previous states. So from 0 to t minus 1. Now, you see that here I mentioned that this is a probability. Why? Because dynamic systems can be deterministic or non-deterministic. So if they're deterministic, then the probability distribution, this probability here, becomes a delta over a specific value. So you're not you don't have a real distribution. You only have one single value that is generated from a previous state. A new state, always the same state, gets generated from the previous state. So every time you go in xt minus 1, in this case, then you will always end up in state xt. If the dynamic system is non-deterministic, then the situation is a bit different, because when you end up in state xt minus 1, then you might end up in a certain xt or in another xt. And so there is a probability distribution here, which is not a delta over a specific value, but it's a real probability. Now you have seen that here we said that the state transition model specifies the probability distribution of a certain new state given all the previous sequence of states. Is this true in practice? Not really. And this is why we have the Markov assumption. So why do we have this Markov assumption? Let me first say what the Markov assumption is. So the Markov assumption says that the current state depends only on a finite fixed number of previous states. And why do you want to have this assumption? Because this sequence is going to grow and grow and grow without a limit until you reach a final state eventually, if there is in your system. So you don't want to keep track of all of that. And so most systems satisfy these conditions that satisfy these conditions are called Markov processes or Markov chains, and this can be, for example, first order Markov, where the current state only depends on the previous state. So this is the case, for example, of the systems that we'll consider in reinforcement learning, and in general of the systems that we normally consider. But there also can be second order Markov systems where the current state depends on the previous two states. So you can see a diagram of this here. So this is the typical RL scenario, while this other one is the case where the current state, so for example x3, depends on both x2 and x1. So we also want to say that we assume generally stationary processes, which means that these probability distributions that we described above do not really change over time. So this conditional probability of getting a certain state from a previous state is always the same for all the time steps. So we don't need to specify a different distribution for every time step. So we say that the transition function can be Markov or can respect the Markov assumption. It's the same. But also the observation, typically, also for the observation, typically the Markov assumption holds. So we generally say that the current observation z at time step t is only generated from the current state xt. So these observations do not depend on the previous observations or on previous states. This results in a diagram like this. So where you don't have any connection between the observations, and you only have the connections between the states and from the state to the observation at the same time step. Okay. Let's move on. So let's look now at one example, which is basically the one that I was giving you before. And you can see that here we basically have a bias network that we are unrolling over time. So the bias network that we have here is giving us a specification of the conditional probability tables for the transition function. So this is our transition function, and for the observation function. So here we have the condition for the previous state being true or false, which will result in the next state for the rain being true with probability 0.7 if the rain was true at the previous state, or rain being true with probability 0.3 if the previous state was false. Again, let me repeat for the I think this is the 20th time that the probability of rain being false here is 1 minus 0.7, and here is 1 minus 0.3, and that these while these values sum to 1 also on the column, but they need to sum per row to 1. This is why in fact this doesn't sum to 1. So here the probability of getting an observation true for seeing an umbrella when rain is true is 0.9, and the probability of seeing it false is 0.1, as it is 1 minus 0.9. And if the rain is false, then the probability of seeing an umbrella is 0.2, and the probability of not seeing an umbrella is 0.8, because it's 1 minus 0.2. As you can see, this column does not sum to 1, but we want them to sum to 1 over the row. So our transition model here is the probability of getting a new state where rain, the next state rain given the previous state rain, and the observation model of the seeing umbrella at certain time step given whether it's raining or not at the same time step. So now also here, as we did for the bias network, we can compute a full probability, full joint distribution of the states, of all the states and all the observations. As you can notice here, this is starting from 0, this is starting from 1, because typically the initial state is not generating an observation for the typical notation that we use. And also because the initial state x0 is nothing else than a prior probability distribution of where the state is starting from, so you don't observe that. So this joint full joint distribution can be represented as the product of all the transitions and all the observations, starting from the multiplying this by the with the prior. So this is the initial state of the model, and then we're multiplying all the transitions and all the observations. So now let's say that many systems do not have a 100% correct verification of the Markov assumption. So sometimes this assumption of being first order Markov is approximate. So of course what you can try to do this case is increase the order of the Markov process, so you can consider more time steps, but also another solution to this problem is increasing the number of state variables so that they become self-sufficient, so you can model the problem in such a way that it becomes Markov or first order Markov. So for example, if you know that the battery power has an effect on the robot velocity, then this battery power information should be part of the state, so that you don't have to keep track of any other previous state except looking at the previous one and consider what is the value of the random variable battery. So now that we described how we can model these temporal models for reasoning over time, then we need to understand what are the kind of inferences that we can perform on these models. So typically you want to perform three kind of inferences. One is filtering or estimation, the other one is prediction, and finally we have smoothing. So with filtering, you're generally trying to compute what is known as the belief state, which is the probability of being in a certain state given all the sequence of all the observations. So for example, we want to know whether it's raining today, given that from the first day until today we have seen a certain sequence of values for the random variable umbrella. So we'll see an example about this. Prediction is slightly different, although related. So now we don't want to know what is the current state, but we want to predict what is the future state given the sequence of all the observations until today. So for example, we want to know what will be whether it will be raining 3 days from today, given that we have seen these values for the random variable umbrella from the beginning until today. Finally, smoothing, which is the concept that probably is the most hard to understand for several people, is basically computing the distribution over a past state. So why do you want to do this? Because maybe you were, for example, performing filtering while you received new observations, but then you see that you got new and new observations and you want to go back and refine what your belief was about the state. So for example, let's say you were receiving all the observations about the umbrella day by day, and you believed that on Wednesday it was raining with a certain probability. Now you see more and more observations, and you go back and you say, okay, you know what, probably last Wednesday it was raining with this probability, which is maybe lower or higher than what I believed to be, given the sequence of observations that I have seen after that. So let's look more in details at all of these processes, and we'll start with filtering. So we want to maintain, in this case, a current state estimate and update it every time we receive a new observation. So how do we do this? So this is mostly a recursive estimation, and this is clear from what is made explicit in this formula. So if we want to estimate the state at t plus 1 given all the observations from 1 to t plus 1, then this is nothing else than performing a filtering process from that incorporates the last new observation at t plus 1 and keeps into account the previous stated estimate. So as you can see here, we're using a recursive formula where this is the previous state estimate, right, at time xt, given all the observations from 1 to t. We are incorporating the new observation at t plus 1, and then all of this is incorporated into this function that we'll see how it's implemented, that gives us the new estimate at time t plus 1, given all the observations from 1 to t and the new one that we got as well, so to t plus 1. Okay, yeah, so we are updating the estimated state distribution using the new evidence z t plus 1. So how do we do this in practice, and how do we get to that recursive estimation? So if we write the probability of a of the state at t plus 1 given the observations from 1 to t plus 1, then this will be the same as getting the probability of the state at t plus 1 given the evidence until time t, and incorporating the new one. Well, we didn't do anything weird here. We just listed all the variables explicitly that we want to take into account. So specifically, we made explicit the fact that we have the observations from 1 to t and the observation at t plus 1. And we know that we can get we can apply bias rule here, and this will be the same as the normalized probability of the new state given of the new observation given the new state and the sequence of all previous observation multiplied by the probability of the new state itself given the sequence of all the previous observations. So what are we dealing with here? So first of all, we can get rid of this term here because we know that an observation only depends on the current state. So this is independent of z from 1 to t. Now we are here updating the current estimate, and here we are performing instead a one-step prediction where we are going from the sequence of all the observations to the next state. How do we compute this? This is going to be just a one-step prediction where, let's go back to this slide here. So we have zt plus 1 given xt plus 1, which is the term that we have here. Multiplied by this one-step prediction, which is the probability of xt plus 1 given z from 1 to t. Now, this is this term here, and we are computing this term by summing over all the possible values of what would be the previous state xt given all the sequence of observations from 1 to t. So given that we don't know this value here, we are summing over all its possible values, and based on this we're using the transition function to compute the probability of xt plus 1. So this is actually our current estimate, or so for which we have some probability. We don't know exactly its value, so we are considering all the possibilities that we would have. So as a summary here, the current filtered estimate of a certain state at time step t given the sequence z sequence of observations t from 1 to t can be computed as a message, the forward message, that is forward propagated by considering the transition model every time and updating it through a new observation. So we are letting the system evolve through our transition model. So as you can see, we are letting the system evolve through our transition model, multiplying the transition function by our current estimate. Let's call this f. Sorry for the overloading of symbols. F here it's not the transition function. The transition function is t, but f here is representing our forward message or our current estimate, and we are multiplying this by what is this? The observation model, observation function. So this is a multiplication of the observation function, the transition function, and our current estimate. Note here that in this notation we have been reasoning about t plus 1 just for convenience of showing the recursive step. But I mean, this and these are exactly the same thing, right? Because this is modeling xt plus 1 given z from 1 to t plus 1, and this is modeling xt given z from 1 to t. So it's coherent. So let's look at one example here. So the date 0, we don't have any, I mean, we're considering again our dynamic system of rain and umbrella, where there is you are in a room where you don't see outside, and the only thing that you see from outside is a person who enters the room with or without an umbrella, and you want to know whether it's raining or not outside. So our state is rain, and our observation is umbrella. So now we want to know what is the probability that at day 2 it's raining, given that we have observed two values for umbrella, yesterday and today. So today we want to know whether it's raining, given that yesterday and today we have seen a person entering the room with or without an umbrella. So of course at day 0 we have no observation. This is our initial estimate. We don't have any bias, so we are our initial estimate is that with probability 0.5 it's raining, and probability 0.5 it's not raining. Now at day 1 we see the person entering the room with an umbrella. So what do? We compute the probability of being in the probability of the state at day 1. So how do we do this? We multiply our prior, for which we don't have a value, for which we don't have a certain estimate, and we multiply the probability for all the possible values that this variable can assume, which are true and false. So the probability of true and probability of false, right? So probability of true and probability of false. So for all these possible values, given that we don't have any certainty about the value of this guy here, we are multiplying this by the transition function. So the transition function is for condition where this is true, right? So in this case, for this case here, we're looking at this row here. Actually, let me use colors. This is our guy. For this scenario here, this is false. We are looking at this guy here. Okay, so in this case we have to multiply 0.5 by this row, the first row, where the probability of rain being true and is 0.7, and probability of rain being false is 1 minus 0.7, which is the term that we don't see here. And in this other case, we're multiplying the probability of rain being true when the previous state was false, which is 0.3 by 0.5, and the probability of this being false is set 0.7. So we do all these computations and we get again 0.5 and 0.5. So we did we let our system evolve here from our initial estimate, and then now we incorporate our new observation. So what is the probability of the state day 1 given that we have seen an umbrella? Well, we just multiply the observation function by our current estimate of the state. So how do we do this? We do the same thing that we did here. Basically, we multiply probability 0.5, 0.5 by 0.9 and 0.2. So why do we choose only this row? Because only this column, because we know that this is true. So umbrella is true. So we need to look at this column here. Now we need to look at this column here, and then we multiply this by all the possible values, all the probabilities for all the values of R1. So we do our computation. We get these values, and we normalize it. So how do we normalize it? We divide by the sum of 0.45 and 0.1 each individual value, and so that this becomes summed to 1, and these are the values that we get. Okay, so this is our new current estimate. Okay, so this is probability of being R1 being true and probability of R1 being false given the observation at day 1. So now this was yesterday. Okay. Now we are at today. What do? We want to compute now the probability of R2 given U1, right? Because we want our system just evolve using the transition function. So we don't have any new observation. We take our previous estimate, this one, and we multiply it, so this one, and we multiply it by the transition function. So how do we do it? Again, we don't have any certainty for the value of R1. We have a probability distribution here, so we take for every possible value of R1, we take its probability and we multiply it by the transition function for that specific value. So this is, again, let's do the same thing that we did before. This is the case where this is true, and this is the case where this is false. So again, we look at the same row here, 0.7, 0.3 multiplied by the value for this being true. Value for this being true. While we look at the second row here, and we multiply it by the value for this being false, which is 0.182. So we do our computations and we get this thing here. Now we take this object here and we incorporate the new observation. So the new observation will be U2, which is again true. So we are multiplying the probability of R2 given U1 by the observation function. So our observation function tells us that given that U2 is true, we need to consider this first column. Consider that here there is another column where this is not U. Okay, so we don't have to look at that, and this would have been 0.1, 0.8. So we don't need to look at that because we have our observation that tells us that this is true. So if this is true, we multiply the same values that we multiplied up here by our new estimate, which is this one, and we get this object here, which we normalize, and we get this probability. So I hope this example was clarifying the doubts that you had. So now, what do we do if we don't have the addition of new evidence? Let's say we want to predict now, given that we have seen yesterday and today the values for umbrella, we want to predict whether 2 days from now it will be raining or not. So what do? We do the same we did in the previous example until today, and then from today on we just use the transition model. So as you can see here, the probability of states in the future, right? So for now, let's say that this is tomorrow. Considering the observations until today will be just the sum over all the possible values that the state can assume for all the possible days that we are considering in the future. So we will consider all these possible values, multiplying the transition function by our estimate. So note that here we're just multiplying the transition function by our estimate. This is not actually our current estimate, but is already our prediction, our previous prediction. At a certain point, this will correspond to our estimate. If we do this in a recursive way, this will become our current estimate, and from there we will multiply the transition function, and then we'll obtain our first prediction. Then we'll take this first prediction and multiply this by the transition function. We'll get our second prediction, and then we'll get our new prediction. Will multiply this by the transition function to obtain the new prediction. So this is how you're going to deal with it. Finally, let's consider the smoothing process. Now, as I mentioned, we want to predict a certain probability for we want to have the probability, we want to estimate the probability for a certain state, a certain previous state, given all the sequence of observations that we got after that. So we're looking in the past. Now we're trying to get probabilities for some state that occurred in the past, given that we have seen new observations. So how do we deal with this? We can split the problem in 2 parts. So let's say we want to compute the probability of xk given the sequence of observations that we got from 1 to t, where k is smaller than t. Okay, so we can split the problem in 2 parts. First, we look at what happened before k, and then we look at what happened after k. Okay, so this first part we know how to deal with it, right? Because this is a problem of estimation. So here we are using our estimate. It's our current estimate. This is the other part is somewhat more tricky, which is how do we compute the probability of here we're basically using the probability of getting a certain observation in a certain sequence of observations in the future given our current state estimate and the past observations. Now we know that this is useless for this purpose, so on the one side we have the current estimate, so f, as you can see here, which is multiplied by what we call b, the backward message. Why is it backward? Because we are trying to get an estimate of something which is this object here that occurred in the past from future observations. Now I'm saying future, but given you got this observation, this is not really in the future. The real thing is that this is in the past, and this is up to the present. So we want to know now how to compute this backward message, or in general this term here. So we do this going basically backward and using again the observation function and the transition function. Somewhat the idea will be, okay, I got this last observation, so this last observation could have been generated by this state. Now what is the probability that this state was generated by some other previous state? Okay, this is hard probability of being having this previous state. Now we'll do the same thing. What was the probability of this previous state to have generated this observation? If this is the probability, then what is then the probability of this state being generated from the previous state again? So we go, as I mentioned, backward, and we start by initializing our backward message to 1, to this thing here, where this is just a vector ones. So how do we do this? So we are now trying to compute the probability of observations from k plus 1 to t, so from Wednesday to today, given the state on Wednesday, which we are trying to estimate. So how do we do this? It's basically by taking our backward message from 2 days after Wednesday, so from Friday, and incorporating, however, the observation from Thursday. So how do we do this in practice? It's exactly what I said before. So we are looking at the observation model and saying what is the probability that this observation was generated by this state, and then we are considering the transition function and say what is the probability that this state was generated by the state that we are interested in. And you are calling this thing in a recursive way somehow. So you are performing this process over and over in order to reach the estimate that you are interested in. So overall, if you look at all the computations, here you're going to just get, again, as I mentioned, the observation function O being multiplied by the estimate that we had and the transition function. So let's look at one example which will be clarifying this a lot. So let's say that now we want to know what is the probability that yesterday was raining, given that we have seen yesterday and today some values for umbrella. So we want to know what is the probability of R1 given U1 and U2. And we know that this can be computed as the probability of R1 given U1 multiplied by the probability of U2 given R1. So how do we compute this? So the probability of R1 given you 1 will be this, we can use bias here, will be the same as the probability of the observation being generated by the state multiplied by the prior over that state. So we saw U1 being true. So we look at this column again. So we take 0.9, 0.2, and we multiply this by 0.5, 0.5, which is, I mean, we know R1 because we computed it from the previous exercise, and we know that this doesn't depend on any observation. So we get these values here. Now we want to know what is the probability that we could have seen an umbrella given that given our estimate of R1. So how do we compute this? We just look at the probability of U2 given R1 multiplied by the probability of R2 multiplied by the probability of R2 given R1. So what are these things here? So this is our transition function, and this is somewhat our observation function, right? So we're considering what would be the next state given our estimate of R1, and what is the probability that this next estimate would generate an umbrella. So we multiplied 0.9 by 1 by 0.7 and 0.3 plus 0.2 multiplied by 1 plus 0.3 and 0.7. Why? Because again we look at this column here and we take 0.9 and 0.2. So this is the case where we don't know what is the actual condition on the state R2. We multiply by 1 because we are stopping here, we're not looking anymore further into the future, and we are seeing at what would be our transition from R1 to R2 if R1 was true, and our transition to R2 if R1 was false. Okay, so we incorporated our observation model and our transition function in here, and we can just now perform our computations and see that here we're multiplying our filtering part, right? Probability of R1 given you 1, right? This is the filtering part, the forward part, this is the backward part, so where we're going from U2 to R1. So we're multiplying again F times B, which is this object here. Okay, so again, let's go just a second back to this to further clarify this issue. We want to compute for smoothing an estimate of what could have been the previous state, a previous state given the sequence of observations until a following state. So a following time step, sorry. So we might want to be interested, for example, in whether it was raining on Wednesday, given that we saw the observations of the umbrella from the first day until Sunday, which is our last day where we took the observations. How do we do this? We can first of all compute our estimate in the forward way as we do usually until our last until Wednesday, and from Wednesday on we need to go backward. And how do we go backward? We look at our last observation, we compute what would have been which basically we try to estimate which state could have generated that observation, and from this estimation of which state could have generated that that observation, then we try to estimate which state could have generated that state. Okay, so we do it in the following way. So we look at this observation, we estimate who might be generating this observation. It could be this state here. Okay, now we have a probability over this final state here. Can we go backward? Yes. We look at the transition function and we say, who could have been generating this state? T plus k. Then we say, okay, it could be T plus k minus 1. It could have been this state. And in this, we also take into account who could have been generating this other observation. And we perform this reasoning backward in time until we reach the state that we're interested in. Okay. So let's move forward a bit. One common temporal model that we usually find is known as Hidden Markov Model, which is a temporal probabilistic model which has some features. Specifically, the state is a single discrete random variable, so if you have more variables, then you compose these to have a single state. You have a transition model, a matrix, and a center model or an observation model, which is a diagonal matrix. So let's look at one example again. Here we are modeling our usual problem as a hidden Markov model. Again, why is it hidden? I didn't clarify this. It's a hidden Markov model because you don't see the real state. So you have an observation model. The observation is what it's observable. You don't see the state. The state is a single state. So here we have our state, and this is our observation, which is the only observable thing. So the state is rain. We have a transition model which is symmetric, as it's described here, and we are computing the observation. We have the observation model as a diagonal matrix, as I've mentioned. Then in this case we have two diagonal matrices, one for the observation being true and the other one for the observation being false. So this is observation true, condition true, condition false, and this is observation false for condition true, condition false. Okay. Let's move on. So computing an estimate or performing smoothing or performing estimation can be very easy with hidden Markov models because you're dealing with matrices. So all of these become just multiplication of matrices in the very exact same way that I have described before. So for computing the forward estimate, you just multiply the observation function, the observation matrix, by the transition function and your previous estimate. Similarly, you can do a similar thing for the backward part, for the smoothing. So you're taking your previous estimate, or actually your future estimate, you're multiplying this by the observation model, and then you're going back in time through your transition function. So it becomes very easy in this way to compute everything. So here in the slides we have some possible optimizations for the forward-backward algorithm, which is an algorithm that allows you to compute the smoothing. I didn't clarify this before, but it's called forward-backward algorithm because you're multiplying the forward message and the backward message. So there are a few improvements that you can get to either occupy less memory while performing this computation, or to be constant in storage, or to be constant in better performing in terms of computation. But we don't need to go into this detail here during this presentation. You can just look at the slide if you are interested in this. So this is why you have all these slides. Here we have few other slides that are related to filtering. Specifically, one kind of filtering that you will find very commonly is Kalman filtering, where you're trying to estimate state variables from some noisy observations. Generally you perform Kalman filtering using linear Gaussian distributions, and I mean, here I just wanted to mention this and say, this is again just filtering. It's exactly the process that we have described before using Gaussian distributions. These Kalman filters are actually used a lot for radar tracking, for acoustic tracking, for visual tracking, and even for GPSs. So you can really say that this is something that is used every day in your normal life. You might be using yourselves, and it's actually very easy to implement. The details are here in the slides. Again, I don't want to go in the detail of it, but it's really just what we described, except that you're dealing with continuous space and you're using Gaussian distributions. I don't want to go in the detail of this because you will see this in other courses, including probabilistic robotics and autonomous and mobile robotics. I just want to mention that this is exactly the same thing that we're talking about in this class. So there are a few slides here that you can look at if you're interested, but you don't have to. So these are not mandatory for the purpose of the class, while you should be more focused on understanding that we can model dynamic systems in the form of probabilities, and this can be done through transition observation functions that describe the evolution of your system, and over these systems you can perform some kind of reasonings that are filtering, prediction, and smoothing. Filtering tells us what is the current, gives us an information about an estimate of the current state given all the observations from the beginning to the current time step. In prediction, we are trying to predict what would be an estimate of the of some future states, given that we have some observations only until now, while in the case of the smoothing process, we're trying to get an estimate of what was the actual a better estimate of the of a previous state given the sequence of all of the observations that we got until now. So Kalman filters, again, there are a few slides over here. You can look at that at home. Similar thing, particle filtering. It's something that you will see. It's used a lot in robotics, especially for localization. So there are localizers that are used in robotics nowadays that are based on particle filtering, and even the one that you will find on ROS for the robot operating system for your experiments with the robot navigation system that is built in ROS. You will see that it's using particle filtering. Again, you don't need to go in the details of this, but you just need to know that this is using really what we described, except that there are few minor things that are detailed in the algorithms that you can find in the slide or in the books if you're interested. You don't need to be interested though. Again. I mean, you should, but you don't need to. So I think I gave already a recap of what we have discussed, but let me repeat it again. We have seen a description and the formalization of dynamic systems in terms of probabilities. We have seen what are the kind of reasoning that you can perform on this. And with this, I think we can close here. And again, if you have questions or doubts, or you want me to go a bit deeper or clarify what are some topics that I didn't discuss well enough for you, just let me know on Slido. This said, we can close this recording here and see you in class.